All right. So now that we've talked about sequences of numbers and sort of how to take their limits and just some properties of them, I want to look at a new use of a sequence now. Right? So let's say we have a sequence given by, oh, sorry, let me change the color here. Let's say we have this as a sequence, all right, as usual, A1, A2, A3, so on. All right. I want to use this to define a new type of sequence, right? So we want to define a new sequence, right? A new sequence which I'm going to call S sub n. And I'm going to call it this for a reason, all right? So here's what we're going to do. We're going to say S1 is just the first term of the original sequence, right? S2 is going to be the sum of the first two terms, right? S3 is the sum of the first three terms, right? And you can probably see where this is going, right? We're just going to keep adding up the terms in a sequence, right? Until eventually, what we are going to do at, say, the nth step is A1. I wanted a capital S there. Plus A2, plus A3, plus, all the way up through AN. And what this is, this is the sum. Hopefully you remember this notation from Riemann sums. It's the sum from k equals 1 to n of a sub k. Right? So all we're doing here is just taking a sequence and we're adding up the terms of that sequence. Right? And we can keep going with this, right? There's no reason to stop at any arbitrary spot. Right? So what we say here is this is a sequence of partial sums. Right? So this sequence Sn is, I guess it's not a sequence, but the sequence of partial sums. Right? And what it is it's the partial sums of the infinite series, right? The infinite series given by k equals 1 to infinity of ak. Right? So what we're doing is finding sort of smaller pieces of this infinite sum. So this infinite sum here is a1 plus a2 plus a3 just forever, right? In fact, maybe I should write this slightly differently. Let's write it this way. So it's this infinite series, a1 plus a2 plus a3 plus a4 plus dot dot dot. Right? This one adds up all these terms forever. Okay? So the reason we talked about sequences is so that we can talk about infinite series. Now, why does that matter? Because the reason it matters is if you look at the infinite series here, what we did is we sort of created a sequence of numbers here that will converge to the infinite series here. Well, the limit of this sequence of partial sums, I should say it this way, the limit of this sequence of partial sums will equal whatever this infinite sum is. In other words, so let's say it this way, if the sequence of partial sums converges to L, then we say that the series here, the first thing we say is that this converges, right? So this might remind you of, doing improper integrals. If the sum exists, if it's a finite number, we say that it converges. Right? So we say that, and moreover, right, this infinite sum here, this is equal to the limit as k, I meant to say n here, as n goes to infinity of these partial sums, right, which is to say that this is the limit as n goes to infinity of Sn, so L, right? So what we're doing here is, in order to compute the value of an infinite series, what we actually have to do is create this sequence of partial sums, so of the finite sums, and just add in one more term, and then add in one more term, and then add in one more term. We want to look at that pattern there and see how it's changing, right? And if that new sequence that we can build, if that actually has a limit, then we say that the sum converges. Just like with sequences, if this sum doesn't converge, then it diverges. So we would say then, if the sequence of partial sums diverges, then the series also diverges. All right, then we also say that it diverges. All right, so that's just some definitions here to get you sort of started on what's going on here. All right. So hopefully this gives you an idea of what's going on. And in the next video, we will do a couple examples of computing sums.